Welcome to the 6th episode of Apple Finch Pudding, your gateway into the world of science. Today's co-host is Korneel Neysens. Korneel studied both biological sciences and electromechanics, and now he works as an operation business process lead for the production of vegetable oils. Welcome, Korneel, but we also have our scientist already. So our scientist for today is Jan Baetens, a professor in data analysis and mathematical modeling at Ghent University. He is an avid math teacher for first years of bioscience engineering, industrial engineers in biosciences, and bioindustrial sciences. Welcome, Jan. Now, I mentioned you're an avid teacher, and you probably don't remember, but I used to be one of your students. And one of the things that I remember is that you knew so many names of students, and that was really astonishing. We were even talking about it amongst classmates on how is he doing this. So now I'm finally in a position to ask you, Jan, how are you doing this?
Well, at that time, I often remembered the first names of the students by just walking around during the practical exercises. Let's say when the students were talking to one another, they addressed each other with their name, of course. And from that, I could already deduce typically the first name. And that's often enough to make people think that you know definitely their name. And then, of course, during the exam, you can walk around. And when students hand in or during the feedback, you also see the written name on the paper and the face in front of you. And typically, once I've seen that, I definitely recognize the people over the next few years.
But just to give the listeners some idea, that is insane. There's like a few hundred people sometimes, and you still...
But yeah, I definitely do not know all names. Definitely not, that's impossible. But from every year, I remember 20, 30 students and their names.
That's a lot. Most professors don't know any names or maybe one or two.
Sometimes it's also caused by the fact that some students tend to attend some of my courses a few times, and that also helps, of course.
Okay.
A few times, is that a lot?
There are records of, let's say 4 years and 8 times exams, and it can be that order of magnitude.
Okay.
That's a record you don't want to break.
Rather not.
And I'm not completely sure, but I think Korneel was also at some point a student of Jan.
In my first year of university, I remember the math that you were giving us with the integrals and the derivatives in the math. It was amazing.
That was essentially the calculus course. That's essentially the one I'm now teaching as responsible lecturer in the different programs.
Okay.
That's a hard one for most students in the first year. It still is. But that's most programs the case. Colleagues of mine, for instance, in the civil engineering face the same problems. That it's a hard nut to crack, that one for most students.
And Korneel, you now work with vegetable oil. Do you still use that mathematics?
I wish I still needed to use it. Unfortunately, no, it's not the case anymore. We don't need to use it day to day. I still remember a case where we work with conveyor belts and also with bottles that fit on it. And from the conveyor belt to the labeler machine, there's an inliner and bottles come from in a row from 5 and they need to go in line to 1 row to the labeler machine. And there we used some integrals and derivatives to define this low speed, high speed of the machine. It was quite a complex calculation, which involved a lot of automation engineers and a lot of civil engineers to crack the nut of that speed. But eventually we made it. So we can say eventually we still use the calculus that is needed there.
Jan would probably just have said, you need to do this, then it's
probably
fine.
Often, of course, there's a huge difference between the math that we are teaching in the first year and also in the subsequent years and the essential math that you then need later on, which is way more complex. Typically for the problems that we address in the first year, that are typically not the true problems you will encounter later on, but essentially what we try to teach in the first year, and that's the most important thing, I think, is to learn students how to solve problems. And we use math as a language for that, but that doesn't mean that you can only solve problems using math. Often, of course, in the world of engineering, there will be some mathematics, there will be some physics, but it might also be a problem from a chemical point of view, so a chemical problem for which you then need some insights into chemistry, but the way that you solve a problem, so the abstraction of the problem and then subdividing it in small problems, which you can then each solve separately, and at the end, let's say, concatenate the different small solutions into a big one. That's essentially what we try to learn the students with those math courses. And of course, the mathematics itself, returns later on in several other courses. And depending on the program a student chose and depending on the final profession that he or she executes, let's say, he or she will still need it on a daily basis or not. Of course, I'm a bit biased. I know people who on a regular basis, let's say weekly basis, really need mathematics.
I can imagine you do as well.
I do as well, but on average, that's definitely not the case. But at least we need people that, if you see the solution of the problem, then at least to some extent what it's about. It's more about the philosophy of solving problems, let's say, than really just computing integrals, because essentially computing integrals, a machine can do that as well.
I do agree, because sometimes you often need more the logic behind thinking on a problem and taking steps into the smaller building blocks on how to go to a solution than the actual integrals or difficult calculus that you need. It's more indeed of a fact of how do we subdivide the problem in smaller problems and stepstones, and how do we continue with it. I totally agree with that. Even in the industry, it's really necessary to do it like that, because if you see a big problem, and everything is always a big complex problem, if you go from that, you're lost. So you really need to do that.
And of course, for most students, that's the most difficult. The student rather has a question as compute rather than a more open question where really a problem needs to be solved. And so what we often do is we just drop the compute part and we let the students solve a certain problem up to the point where then really you need certain specific techniques to solve something, because often those are so specific that it's more efficient to use a computer for that nowadays than do it yourself. But solving the problem up to the point where you can compute something, that's the most challenging part, and that's also the part where most students are struggling with.
Before diving into the math of it all, I'm going to start with my first question, and that's actually for a science joke or an anecdote or a fun fact. So I don't know, Jan, do you have a science joke or a fun fact or something?
You also mentioned it could be an anecdote. There are two things, I think. First of all, many people think, okay, it's mathematics, so it's certain, and that's definitely not the case. So in many cases where we are involved, it's not because you use mathematics that the outcome of something will be certain. And secondly, which might be a bit more surprising, but my track record in the first year of secondary school, so that's already a while ago, I barely passed for mathematics. So yes.
Really?
Yes.
Wow.
I would not have expected that.
No, really not.
Yeah, because there, at least in my time, it was more about really those drill exercises. You had to do 20 times this, 20 times that, and so on. So at that point, I barely passed. Now, of course, over the years, that changed. Just to indicate, it's not because you encounter people now really into mathematics that from the very beginning it was like that. So it's also something you can learn, and you can learn to appreciate depending on the viewpoint you take.
I think that's a really nice thing to know, actually, because a lot of people struggle with math and then they think math isn't for me, but that's not necessarily the case.
I should have checked, but I think in the first year secondary school for mathematics, I had 51% only. So you would not expect that.
No, I definitely wouldn't. And Korneel, do you have a fun fact or a science joke or an anecdote?
When I walk outside, I'm amazed by trees. I really love trees. I adore them, really. And the fact that I want to say here is a tree can grow, but we also know that it has its limits. We know that the stop on the growth of trees is mainly because of the gravity. It's as simple as that. It's not because of breaking, of mechanical damage. It's not because of the water and whatever is going there. No, it's because of the gravity that it's not able for the water to go higher, so that the leaves close their stomata and then they cannot do the photosynthesis quite well, so they don't grow anymore, and they invest more in thickness and in growing fruit than in growing. For me, it's a fact that amazes me, as simple as that. Gravity rules everything, really. I'm really amazed by it.
I'm just going to pile on that a little bit because my PhD was on foliar water uptake.
Nice. Yeah.
And they actually hypothesized that the giant sequoias in California, they know that they absorb water with the leaves, and that might help them to become larger because they overcome some kind of gravity because they have water that enters at a higher level.
Yeah, of course. Oh, really? That's a cool fact to add on that. that one. Nice, thanks.
And I also have actually a joke. I hope it's funny. So a biologist, an engineer, and a mathematician are observing an empty building. And at some point, 2 people enter the building, and a bit later, 3 people are leaving it. And the biologist says, okay, they procreated, they reproduced, and now 3 people are leaving. The engineer says, no, we must have miscounted. If 3 people are leaving, 3 people must have entered. And the mathematician says, so if 1 more people enters the building, then it will be completely empty.
Oh, man.
It was a bit stressful for me. I was thinking, should I tell that joke when Jan is the scientist? I wasn't sure.
You succeeded.
So that being said, Jan, mathematical modeling is the subject you work in. Everyone has an idea of basic math, but what is mathematical modeling in its most general form?
It's a way to describe processes, can be biological processes, natural processes, environmental processes by means of mathematics. So you have a biological process, for instance, growth of a tree, to stick to the trees for the tree huggers among us. You have a tree, you want to model its growth. Okay, you observe the process, and then based on your observations, you try to come up with a few equations that describe the growth of that tree. And those equations together with, let's say, the initial height of the tree, some environmental characteristics and so on, make up the mathematical model, which you can then use to run simulations. For instance, how will my tree look like in 10 years? How will my tree grow if, for instance, the air humidity drops by 50%? How will the tree grow if the average temperature increases with 1 degree centigrade or something like that? And that enables you to conduct scenario analysis. And that's, of course, a very simple problem. You can make it more complicated. For instance, think about the evolution of the pandemic. You can capture that with a mathematical model, and then you can ask yourself the question, what if certain measures are relaxed the 1st of March versus the 1st of April? What is forecasted that might happen then with the evolution of the pandemic? And in that way, you can hopefully get to more meaningful and underpinned decisions in the end. So very simple. It's just a mathematical description of some process. But of course, that mathematical description, depending on the process, can be very complicated. It can be very straightforward. And once you have that, you can run simulations to obtain whatever you want.
So if we put like the most simple example we can imagine, for example, we observe that the tree grows a centimeter every day. And then you just say it grows a centimeter every day. We model this in 5 days, it will be 5 centimeters taller.
Yes.
Then we add extra constraints like if humidity drops, it will grow less.
Yeah. And if you have data on that, you can incorporate that so that you can run different scenarios. If the temperature drops by 2 degrees centigrade and the air humidity increases by 10%, I forecast that the tree will have grown by 8.5 centimeters in 5 days instead of 10.
You always need those data from a previous observation.
Data or knowledge?
I was going to ask that because when you start from nothing, there is an input, you have a process, there is an output, and basically you are describing the process. But there are a lot of parameters that you can incorporate in the process, and then it can become complex quite quick. So how do you pinpoint what you need? Because also for COVID-19, there is climate, there is people, there is social behavior, there is anything that you can incorporate there. But where do you pull the line, or what do you drop? What do you keep in your model?
The guideline there, or the rule of thumb there is, it should be complex enough to capture to reasonable extent the process you're interested in to required accuracy, but not more complex than that. Because indeed, even for the growth of the tree, you can include the climate, the whatever. You can make it always as complex as possible, but there it's a matter of being pragmatic to some extent. And it's also a trade-off between the time you have to develop a model and the resources you have to develop a model, and on the other hand, the accuracy you want to reach. For instance, the COVID models are the result of a pragmatic balance between those two things. A perfect model doesn't exist. All models are wrong. But among the wrong models, you need to select the one that is the least wrong. That's essentially what you should do. And the model you typically build on the basis of data, if data is available, or on the basis of knowledge. Yeah, for instance, you know a few laws by Newton or other physical laws. You don't have to reinvent those. knows, you can just use those laws. So it's essentially a combination of data and knowledge, as much as possible knowledge, because then you can make meaningful changes to the models. But of course, not everything is known. For instance, what is the impact of temperature on the spread of COVID-19? There is knowledge about that in terms of data, but there is no mechanistic explanation in terms of an equation for that. So you need to use data. That's the only thing you can rely on.
So one of the things you said was the model needs to be adapted to the question you're asking.
Yeah.
And is it like something, if you want to go to the COVID models, for example, COVID will spread less when people have to stay inside. And as a result, just to say something silly, dogs will be more often in the garden and not in parks because people don't go with their dogs to the park. But that's not relevant to your model. You don't need to include the dogs. So that's information you don't need.
That's information we don't need. And that's also something we won't be able to forecast. Let's say you then focus on, we want to forecast, for instance, the number of hospitalized patients per day and the number of infected cases per day. And that's what you want to get out of those models. All the rest, you don't give as much attention.
To summarize, mathematical models can be based on knowledge of certain things like gravity or stuff we know. We also can use data to base the models on, and they need to be adapted to answer the questions we want to answer. But then my question is, what kind of models are you working on? What are the questions you are asking?
Yeah, so that's of course very diverse. If you go to the shop of mathematical models, that shop nowadays is filled with everything. So it's really a huge shop, let's say.
I don't know that shop. Where is it? Is it around the corner somewhere?
No, it's somewhere in Ghent, I think.
Okay.
So it's really the diversity in mathematical models nowadays is really huge, way bigger than before. And that's mainly due to the fact that computers make data-driven models way more within reach than before. Now we can process huge data sets in a matter of seconds. Let's say 20 years ago, 30 years ago, that was definitely not possible. That makes that there is a whole diversity of models there. For the research that I'm conducting, we try as much as possible to build, develop, and analyze models that are what we call mechanistics, so that offer an explanation of the process that you're describing. So that are typically models that are not completely data-driven. No, you want as much as possible to include physical laws, biology, chemistry, earth sciences, and whatsoever in the equations you finally formulate. So, for instance, you use the diffusion law, you use the law of Fick, you use Newton laws, you use whatever you get from physics, chemistry, and so on. And that's your basis. And if some part is unknown, you might try to get information on that by using a data-driven part, let's say. That's the general focus. And within that type of models, as much as possible, we try to focus on models that allow you to forecast not only evolution through time, but also evolution through space, typically at micro scale. So where we, for instance, instead of just working with density of vegetation, we try to model the actual position, size, diameter of individual trees. So if I have a piece of land here, there are a few young trees scattered all over that piece of land. There are models that enable you to evolve and to simulate how that piece of land will change under certain conditions over the next 100, 200, 300 years and so on by tracking every tree individually.
And how do we need to imagine that? Do you see the trees growing on your screen, or just equations that you're seeing with the distribution?
The first one, essentially, if you want. Yeah, to render that to the screen, that's not that straightforward, but essentially that's what's happening. So for every tree separately, you track the diameter, the length, the foliage coverage, and so on. So that's possible. So what we did do, for instance, a few years ago, that was with the Dodentocht. We constructed a model that enables you to simulate scenarios where you track every individual participant in the Dodentocht, so in the 100-kilometer endurance event. And with that model, you can run scenarios in such a way that you can really see the movement of the individual hikers along the 100-kilometer trail. And you do those simulations at the basis of the individual. So you track every individual, its walking speed, its direction, which is in that case pretty straightforward. But anyhow, the time it stopped at a different checkpoint and so on, because in that way you can simulate the entire spatio-temporal evolution of such an endurance event. And if you have such a model, you can then answer questions like, what is the most optimal starting procedure for such an event? For instance, it used to be the case that all participants started at the same time in the narrow streets of Bornem. That's a small town in Flanders. And what you then got is that the starting procedure lasted for more than 1 hour. But if you have such a model, you can then verify what will happen if, for instance, we start at 2 locations in the city, or if we start in 3 different groups, or if we start in such a way that the slow hikers are in front, the fast ones are at the back of the group starting. And in that way, you can run those scenarios, let's say, you can analyze the outcomes, and you can then advise the organizers, for instance, of the Dodentocht, okay, based on this model, based on these simulations, we advise you, for instance, to start in several groups outside the city center, because that will lead to the most optimal starting procedure and also not create bottlenecks later on.
And what do you need for this model? For example, did you need to track hundreds of people that did everything beforehand? And then based on those data, you constructed the model?
Yeah, a few physical laws, of course, about the movement of people. And then because those laws and those equations involve still a few parameters, let's say, we had, I think, for 7 or 6 editions of the Dodentocht, all tracking data of all participants.
That's a lot of data.
It's indeed a lot of data, because if you do the Dodentocht every 10 kilometers, your time is registered. And we had that for all participants for 6 or 7 years. And you need that, of course, to get the parameters in such a model right.
How many participants on average per year? Do you know that?
About 15,000.
Okay, so 15,000 times 6 or 7. Yeah.
If I dummy everything down, so in fact, you need certain parameters, certain equations, and then your data. Then you combine everything, the equations together. And then you have X plus Y times Z quadrupled, whatever. That gives some solution. And based on that, the result of your model.
Not really. So you have to additionally do that for every time step in your model. The model, the simulation progresses with a time step, let's say, of 1 minute. And for 1 minute, you have to recompute the position of every hiker in the simulation. And that you have to repeat for every minute in the 24-hour duration of the endurance event. So you recompute the position and the speed of every hiker for every minute for those 24 hours. And like that, you can reconstruct a realistic average Dodentocht dynamics. And then you can start to play between quotation marks. What if we would have started in 2 groups? What if, and so on and so on.
Like you explain as well, you use mechanistic models. So that means that you try to use equations based on laws of nature and stuff like that to model what is happening. But you also need data. The other way around is black box models. That's something you don't use, or not that much. Maybe just in general, what do black box models mean?
Black box models typically do not give you any insight into how the process that you are modeling actually work. While with the mechanistic model, you get those insights. Now, sometimes in those mechanistic models, there are, let's say, terms in those equations which you cannot really pin down based on your knowledge of biology, chemistry, physics, and so on. And those terms you can then try to derive from data.
That's the parameters you said before. The parameters that you're trying to estimate based on the data, that's actually a tiny black box model in your complete mechanistic model.
Yeah.
If you dummy down the black box model, you have an input, you have an output. If you have that 100,000 times, then you also can pull some statistics. I can see, okay, this is normal. Here we have an outlier and this is not normal, without knowing what in the black box is happening. But even then you can see based on your data, what should be the outcome. But you apply it sometimes in your complex models because you don't have the correct equations then available.
Indeed. For instance, we have seen for the Dodentocht that the hiking speed depends on many things, but amongst other things on the age. And then, of course, there is no equation that really connects, on the one hand, the age of a person, and on the other hand, the hiking speed There is no physical law for that. And if you need finally to be able to derive the hiking speed of every individual hiker, you need a number for that. So then the best thing you can do, as there is no equation directly relating age and hiking speed, the best thing you can do is get as many data on that as possible, and using a data-driven approach, get a reasonable estimate for the hiking speed of a participant of an age 54, for instance. And with that, you can continue.
And does that also go back to the complexity issue that you mentioned? Because you could maybe look at when people get older, their muscles start deteriorating a little, and you could try to incorporate that, but you're making it so complex, answering questions you don't need and making it almost impossible to calculate.
Yeah, essentially, you could, for every hiker, try to model that entire organism. But yeah, that's anyhow impossible for one organism. So you definitely cannot do it for 15,000 organisms at the same time. And you won't gain a lot by doing that. And if you have that many participants, you can get an overall idea of how does age affect the hiking speed by just using your data. But as much as possible, we start from a mechanistic model, so a mechanistic explanation, because there are meaningful parameters. For instance, there are laws, and that is known from physics, that give you an indication of how the hiking speed depends on the crowdedness. So how crowdier, how slower the people often hike, and there is an empirical relationship for that. And if you have a parameter that captures that, you can, of course, then look at scenarios. What if we start not at the city center, but outside the city where the streets are way wider, so that the density of people around you drops, because that effect you can incorporate in that parameter. Yeah, and if you have an equation with that parameter, you incorporate that effect of halving the density, for instance. You can incorporate that in that parameter, and you can run a scenario where you widen the streets by factor 1/2. And that you won't be able to do with black box models, because you don't have a clue which bell to turn or which whistle to blow, let's say. But with mechanistic models, you have that. Yeah, for instance, if you have a simple diffusion equation, you have the diffusion coefficient in that equation. If I tell you now you need to simulate the diffusion process for another type of liquid, which has another diffusion coefficient, which is double than the original one, you can just double the diffusion coefficient. If you have just a black box model of diffusion, you get another liquid, you won't know which wheel to turn, so to say, to get a meaningful insight into that.
So in case of the Dodentocht, 15,000 people are starting, and that's what happens. But if you use a black box model, you just know what happens when you start with 15,000 people. If you want to start with 7,000 people, you don't know how to do that. And because of a mechanistic model, you can just include this in the equation. We start with less people, what happens?
As much as possible. For instance, also with the COVID models where we worked on, the infectivity of the variants changed over time. So the first variants didn't have an as high infectivity as the later variants. So if you have a mechanistic model of how COVID spreads in Belgium, you can then just, depending on the variant and depending on the proportions by which the different variants were present in Belgium, you can change the infectivity in your model equation in a meaningful way, and you will never be able to do that with the black box model.
Maybe to go a little further in your COVID models, because that's also really interesting. So, for example, you modeled this for Belgium. Would it be a big difference to model it for a different country? Do you need different parameters?
No, essentially the model can stay the same. The input data is different, and also the data that we would need to get the parameters right is also different. The model structure can be exactly the same, but for instance, the average residence time of people in the hospitals is country dependent. The death rate is country dependent. Also, the time at which measures were taken is country dependent. So if you have that structure and you just tune the parameters and tune some of the inputs to the country in question, you can just use it for that other country. That's no problem.
So, for example, in Italy, you have a lot of smaller streets. You can just put that in your model that people will be closer to each other when they're in the streets.
Yes, you could do that if you would look at it at that level. Yes.
Yeah, I'm just giving some example. Well, that's actually a good question. What did you model exactly about COVID?
We were most interested in three things: hospitalizations, deaths, and confirmed cases. But deaths and hospitalizations go somehow together. So that's hospitalizations and confirmed cases. In Belgium, from the outbreak of the pandemic, so March 2020, we've been following that up to the end of December 2021, where we gradually improved and extended the models to take into account the variants, so Delta, and then later on also Omicron, vaccinations. That was another thing that required us to extend the models, and also the spatial differences. So we started with a national model, just working at the level of the Belgian population. And that was, in the end, also reformulated in a spatial way so that we are essentially now have a model that's operational at provincial level. But that's a fully coupled model, meaning it's based on the mobility of people in Belgium between every arrondissement on an hourly basis. So it's a huge model, which also is quite data hungry because you need the data of how people are moving on an hourly basis between every pair of arrondissements in Belgium. So from a computational point of view, quite intensive, but it allows you to investigate the effect of local outbreaks. What if there is an outbreak in Ghent? What if there is an outbreak in Antwerp? Or local measures, for instance, if there would be a lockdown in Antwerp only, what is the effect in Brussels? What is the effect nationwide? And so on. An effect typically on death counts, confirmed cases, and hospitalizations.
What did you need to measure to model all of this?
So first of all, mobility data, knowing from people how they typically move over time on an hourly basis. So that's based on cell phone data from a main telecom provider in Belgium. Then also the counts from the hospitals, meaning confirmed number of cases, hospitalized number of cases, but also number of people in ICU, number of people that died, number of people that recovered, numbers of people vaccinated with 1 dose, 2 doses, boosted, yes, no. So also that data set, then also information on the serology, so percentage of people over time with antibodies for COVID in their blood, the entire demography of Belgium, so nationwide, how does the demography look like? Then also data on how often people from different age classes interact with people from the same age class and with people from other age classes, because COVID and the spread of COVID is really age dependent, and also the severity of COVID is really age dependent. The model we developed, but also colleagues of ours in Hasselt, for instance, distinguishes between 10 age categories. So 0 to 9, 10 to, and so on. And for every age category, you need an estimate of the number of contacts per day with individuals from the same age category and from other age categories. And that also then depending on the type of contact. So are there people encountering each other on the work floor, in the grocery shop, on the public transport, at home, and so on. So it's rather data hungry, but still it's a mechanistic model. But in that mechanistic model, there are quite some parameters that you need to infer from all those data sets. And for instance, also from the hospitals, typical time spent by people in ICU, typical time spent by people in the hospital, all that kind of stuff. And this all age-based. So age-based, first of all, you need to discriminate between the different age classes. And then also spatially stratified, we then call it. How do these parameters depend on space? Because hospitals in Hasselt have different policies than hospitals in Bruges, for instance, which made that the residence time of patients in Bruges was different than the residence time of patients in Hasselt. And if you have a spatially stratified model, you want to account for that to some extent.
What takes the most time then? Because what you're saying now is, okay, there is a lot of data used. There is a lot of time spent on probably crunching the data. There is also probably a time you need for, I want to have my model set up. What is taking you the most time?
For COVID, but I think that's in general the case for the models that we are developing, setting up the model. Essentially, as you are mentioning, once you you have the data, which is also not always that straightforward to get the right data. But crunching the data, nowadays, that's not really an issue anymore. But setting up the model and then incorporate the right data in the model, that's taking long. For instance, the development of those COVID models, that was an ongoing work from March 2020 up to December 2021. Because you have a model version, call it version 0. Oh, there is a new variant. Version 1.0. Oh, there is yet another one. Oh, there are vaccinations. Oh, there are new measures and so on, and how to incorporate all that. So that model development and really setting up the model and keeping it up to date, that definitely took the most time. And also with the Dodentorch, for instance, setting up the entire model, that takes the most time. Transferring, for instance, those models to another setting, which is similar, of course, for instance, to another country, is relatively straightforward.
Yeah.
But your model is only as good as the data you get.
Yeah.
But for example, the data that you mentioned, the contact between people from different age groups, how do you get data on a child visiting his grandparents?
Luckily in Belgium for that, there were some good resources based on surveys that are organized on a relatively regular basis. But of course, those surveys involve only a sample of the total population, but that's what you have. Yeah, and essentially it's a kind of extrapolation you then do to the entire population. But what else can you do? It's better than nothing. Otherwise, it's just guessing, while based on those surveys, you can make a more meaningful estimate, let's say. Also, for instance, the mobility data, as I mentioned, we have the mobility data of one main telecom operator in Belgium, but there are, of course, others. So, let's say we covered only 1/3 of the population carrying a cell phone, but if you have 1/3 out of 10 million or 11 million, let's say that's sufficient to make sure that it's representative.
And might it be a difference, for example, in demographics, if you use a very expensive cell phone company or a very cheap one, that might have a different effect on how people move, or not really?
Could be, but to be able to answer that question, you essentially would also need the data of the other telecom providers so that you can compare. I indeed guess that there might be a difference.
And what has come out of this? What has happened based on your model? Were they able to change some guidelines because of it?
Well, so at some point at the beginning of 2020, we joined efforts. So our group, the group of Neil Hens and the group of Kurt Barbé in a kind of COVID-19 modeling consortium. Because those three groups, and then also a group of the University of Namur, had developed those models. Now, this might seem weird to have different models for the same thing, but it's the way it is. So there is not one way to model the spread of COVID-19. No, there are probably 10, 20, or even more ways to do it. And if you then want to account to some extent for what we call model uncertainty, the fact that, you choose a certain model structure, so that's also introducing a kind of source of uncertainty. And if you want to account for that, it's better to combine the results of different models in what we then call a model ensemble.
Sounds very fancy.
Yes, indeed. We combined the results of the Ghent model, the Hasselt model, the VUE model, and the Namur model in reports for, let's say, the different advising bodies in terms of COVID-19 during the pandemic.
Is there then also a comparison between the combined model and the model separate? Because if you have the combined models and we see compared to each other, there is no difference based on a statistical test that we do, yes or no, then we know, we don't need to combine it, or don't we do that?
We did that often graphically because we wanted to avoid to dig too much into the numbers, because there were so many uncertainties from about either the data, the disease characteristics, the policy, and so on. And the fact that we had to forecast weeks ahead, even 2-3 months. We didn't want to pin down too much on, we forecast in 3 months on that day, 100 hospitalizations. So those models are very good for, let's say, trends. Yeah. What do the trends look like? Can we expect another peak? When more or less can we expect it? And how high will it be more or less? But 10, 20, 50 hospitalizations, less or more, everything is possible. But what we were mainly looking at, the different models, do they coincide in terms of trends? So meaning, do they all predict a next peak? Yes, no. Do they all predict the peak more or less in that period? Yes, no. And that way, we were typically comparing between those models. So more from a qualitative point of view rather than a quantitative point of view, because there were so many uncertainties and the fact that you had to forecast weeks ahead. And the fact that in the spread of COVID-19, humans were involved and humans are very difficult to capture in equations. It's easier with, first of all, things that are not living. So essentially in that respect, the life of a civil engineer is easier because everything is dead over there. The life of a bioscience engineer is more difficult in that respect, and especially if humans are involved, because humans do not always behave rationally according to equations. And that's an issue, for instance, if you need to implement measures that are imposed by, let's say, the government, by policymakers. How are people going to react on that? How is that going to influence the mobility of people? That's not that straightforward to estimate.
And also probably on some point, people just get tired of the restrictions and they start reacting totally differently than they did the first time.
Yeah,
exactly.
Yeah. And what we did with that consortium over the last 2 years, from time to time, we made confidential reports, but we also compiled public reports where we just balanced the different scenarios against each other. For instance, I'm remembering a case. It was the fall of 2020, where there was a discussion ongoing. Okay, are we going to relax the measures, yes or no? And there is one report, for instance, a public one, where you can clearly see if you would have relaxed the measures in, when was it, October, November 2020, you would have had a huge peak later on, which has convinced or which has made it possible to underpin the fact that then at that point in the fall 2020, at some point, more strict measures were suddenly taken because we saw the problem coming, of course.
This is quite big because this is governmental decisions. The modeling is also used for universities and studies and papers and such. A stupid question, and I'm also an industry person. Is it applied in industries? Is it applied in processes? Can we use this?
Which model specifically?
Any mathematical model. For example, I'm in the business of vegetable oils. We have an input of crude oil and we want to have refined vegetable oils. Our yield needs to be always higher and higher. So we get always the push from management. Our yield needs to be better and better and better. There are certain parameters that are in the process that we need to adjust depending on what the input of the crude is. If there is more moisture in it, if there is more contamination of chlorophyll or carotene or whatever, if there is certain parameter that we need to adapt depending on the origin, depending on the climate, on the temperature, on moisture, on whatever, should we be able to make a model on it if the infeed is this, or if we need a high yield based on the data that we have already, this and this and this needs to change in the process, and voila, our yield can be higher.
It doesn't seem a bad idea to consider that, because otherwise it's really trial and error, more or less, and based on experience.
Yeah, that's a fact, yeah. And mostly in industry, that's where we are. We are at trial and error, and we see if we lower the pressure a little bit more nearly to the vacuum, or we put the temperature some centigrades higher, then we have a better throughput and a better yield. So sometimes it's really trial and error. So that's the point.
That, of course, depends on how complex the production process is. But essentially, I'm definitely aware of cases where they use models to optimize whatever, the efficiency, the output, something, or to look at what might happen if. But it really depends on the process that's occurring. Is it well described? Can it be captured by a mechanistic model? Yes, no. Are data available? Yes, no. How much time/money is available to construct such a model? Because, of course, that's taking time, so that's costing money. And for industry, it's often cheaper. Okay, today, let's try this. Tomorrow, let's try that. And yes, we are lucky. So we can go ahead for another 6 weeks. And then, okay, new problem. What are we going to do? Okay, try this. And like that, it moves on, of course. But there was something that we've done also with fruit juice, for instance. So if you take a bottle of fruit juice, there's some air on top of the fruit juice. And then based on the amount of air or something like that, I don't remember the details because that's from a while ago, but you influence the sell-by date of the fruit juice. And you can capture that in equations. So you can see, okay, what if those things are possible?
I might be wrong, but if you're unlimited in time and money, aren't you able to model almost everything?
Probably if you make wise choices, yes, to some extent, yes. But the problem is a trade-off between time, money often. What money do you have without any guarantee that it will work? So we can only say based on experience, those models are operational, for instance, in the pharmaceutical sector. They also often use them to optimize the production process of pills and so on. Also in wastewater treatment, for instance, there are models that capture the entire wastewater treatment process so that you can see beforehand, okay, it's going to rain, so my inflow is going to increase. What can I expect over time for what concerns the effluent in terms of how long it will take to get effluent that's treated? It's possible to do that. And those models, for instance, are fully operational. And also for the sewer, for instance, there are those operational models that really allow you to go as crazy as you want. And definitely, yeah, also with those industrial processes, it's definitely possible, but it takes time to develop those models.
If we assume you know the mathematics and you have the model, what do you need? Because I assume that generally the models that you're making, you're not able to run them on your laptop.
No, we use typically the high-performance computing infrastructure of Ghent University. So let's say a computing cluster. But yeah, that's not for all models needed. You know, for the COVID model, you definitely need one like that. Not really to run it, but to get the parameters right. Once you have done that, and that can take up to a week, then you can run it relatively easy. But for most other models that are not too complex can be run now on a nowadays computer. But if you really need many simulations, many replicates and so on, then often a cluster is needed, yes.
So some kind of supercomputer, and it still needs to run a week before you get your data or your parameters.
Yeah.
Because people always think we have computers now, it goes so fast. And if you have a very expensive one, it will be finished in like a few minutes, or if you're unlucky now.
No, so for instance, for the COVID model, yeah, we stopped it after 3 days, so 72 hours essentially. But then the issue is in such a model, there are a few parameters. The model simulations take a while. And you want to retrieve the model parameters in such a way that the model outcome agrees as much as possible with what is observed. And to do that match is mathematically a challenging problem. It's an optimization problem, which in the course in the first year we tackle just by pen and paper, let's say. But for the true problems, you need a computer to find the optimum, meaning what are the optimum parameter values so that the difference between what we observe and what we simulate is minimized. And that takes 72 hours. And then even it's not yet the true optimum. So you might need another few days more, but we just stop it after 3 days because you can go on forever if you would like.
And you can also have a false optimum, that you have like a dip in your data more or less. How do you know that as you're modeling that you're not really at the optimum?
That's then our trial and error. You do that procedure a few times or in parallel. You repeat the search for the optimum a few times on different computers for those 3 days. That's often the hardest nut to crack from a computational point of view. Once you've done that, you can run the model, and that's typically computationally not that demanding. Of course, if you go to those detailed three-dimensional models that, for instance, simulate the flow of fluids, that can take forever. But for instance, for the COVID model, it's pretty straightforward. But as soon as you go to 3 space dimensions, whatever you do becomes very computationally demanding, but not impossible.
So you need parameters, you need your equations, you need also a translation to your programming, to your computational software. Is this literally programming, JavaScript, etc., or is it mathematically programming?
No, it's whatever language you prefer. So Python, Julia, MATLAB, name it, yeah.
And Jan, you work in academia. Korneel works in industry. Why did you choose academia? And what do you like about academia so much?
Not the working hours, because I have to say I arrived back home at 10 to 8, so that definitely not. But it depends on the period. It's not always that bad. But I think the flexibility and the freedom to some extent to explore, let's say, that's, I think, the most important point for me. Of course, there are deadlines, but those deadlines you typically impose on yourself. It's not like in industry, we don't have to be happy with some dirty work. I don't want to be too negative about industry, but I know from colleagues of mine who went to industry that the efficiency is often more measured in terms of true output of a machine or whatsoever. And if you can increase the efficiency with a dirty trick, it's also fine. We try to avoid those dirty tricks. Of course, that might be a bit cumbersome. It might take us more time than you would expect to get to some tangible result. And that's also for us sometimes a trade-off that we have to make. But there, I think it's interesting that we still have that flexibility and that freedom, not really to optimize always like you have to do in industry, and that you get the freedom to get the answer really right, let's say, with the best possible means available at that time, given, of course, the boundary conditions there are. Essentially, the COVID models that have been developed over the last 2 years, if you would take time and if you would redo it, you would probably do it completely in a different way. But yeah, they did what they had to do and they have been useful. So, okay. And that was, I have to say that also, so the COVID period and the development of those models has been rather atypical. The models had developed on the fly, almost real time, to be used almost real time, to provide input to other places almost immediately without having the time to do a decent sensitivity analysis or other things that are really established normally in model development.
Did you think that is okay, or were you worried about it?
We were worried about it, but you have to row with the means you have at some point. And that's why also in those reports, and never we tried really to focus too much on the numbers. We want to get the trends right. And COVID is difficult and way more difficult, for instance, than essentially predicting the weather. You know, predicting the weather is essentially straightforward. It's just physics. There are no humans involved. And how often still you cannot trust the weather forecast even for the next day. For instance, yesterday they were predicting at my place, I think 12 millimeters of rain, and we had 2. So then my conclusion would be the model they are using is wrong.
So are you saying that your models are also wrong? Because, yeah, you said all models are wrong.
Yeah, they are definitely wrong.
If there's already a big mistake on the, I'm just trying to say your words, a simple model of weather forecast, then the error on your models that are more complex must be a lot bigger, or not really?
I think the weather models are way more complex in structure, but the process they are capturing is also complex, but that's only physics. In COVID, you have to deal with physics, biology, and then also psychology. And you have to capture those 3 things in a model. Yeah, and the model structure we have is, of course, way simpler than a weather model, but look at how badly the most advanced weather models sometimes behave. Yeah, and that's why sometimes also in the weather forecast, they mention, according to the German model, the sun is going to shine, while according to the UK model, it's going to snow, for instance. Sometimes those models do not agree. And if you look at the forecast, even for the next 24 hours, for what concerns rain, for instance, it might be completely off. And if you look at, for instance, meteo.be and you look at the uncertainty envelope, after 5 days, it's becoming huge. So how on earth can you expect a COVID model to get accurate numbers for the next 3 months ahead? That's practically impossible. So the thing you can get right are the trends and the orders of magnitude. And that typically worked. But of course, in industry, and that's definitely true, if you have an industrial process, you want to get the numbers as right as possible. But there, of course, an industrial process takes place over minutes, seconds, whatsoever. So it's a completely different story. And there you can get the numbers typically way more right than you get them over the longer time periods, and definitely if humans are involved.
And so, yeah, you're a mathematical modeler in academia. Based on what you said in the introduction, I assume that wasn't the job you envisioned when you were a child. So what did you want to be when you were a child?
What was it? Pilot. But then ice problem, so that didn't work. So then civil engineer, but then there was still the entrance exam in different parts. And I only went for the first part. I didn't go for the second part because essentially it was at the beginning of July and I was a bit fed up with it. So I didn't go to that. And at some point in September, I decided, okay, there's still another type of engineer, apparently the bioscience engineer. So I started that track.
So actually you were just sick of the exams and was like, I'm going to go bioengineer.
Yeah, exams in the holiday period, that's not essentially my cup of tea at that time.
No, I get that. So, and at this point, can you imagine not being a scientist? Like, what would you be if you weren't a scientist?
I like cooking, so maybe cook. On the other hand, I have to say also in my childhood, I did quite some things with plants. So I had a small tree plantation. So maybe that was also an option to do something with trees or with vegetation anyhow, but not at academia, so not within a scientific environment. But yeah, who knows?
Based on that answer, actually, do you model a lot of plants then? You said you model individual trees in a forest. Is it something you do often then?
That was a very small project, a very recent one, but that's something we typically don't do that often. Essentially, for us, that's just a kind of, applications, whether it's a tree that grows or whether it's an animal that grows or whether it's whatever. It doesn't really matter because the underlying mathematics is often similar. Like, for instance, the Doorntocht model, that mathematics can as well be used for something else. The COVID model, again, if you would reformulate it a bit, you can use it to simulate the interaction between organisms. So in the end, what we call X and Y, that's often the end stage. And it's more about the mathematics underlying it. It often depends on the people to whom we talk or the people that contact us for input or with problems. For instance, the fruit juice problem, that was a problem apparently somewhere in an industrial plant. Is it possible to model that? Yes, it's possible. And okay, you use some mathematics that we also use somewhere else, and then it becomes fruit juice instead of a tree.
But it's not like you're missing your connection with plants and trees.
No. Definitely not. And I have plenty of connections still with plants and trees. And that's not the problem. And I'm definitely not only focusing on modeling plant and tree growth. Definitely not.
I think we can round up more or less. Do you have a take-home message actually for the listeners?
Yeah, maybe often people, as soon as you mention the word mathematics, they almost run away immediately, because they think it's complicated. But as I mentioned before, it's more a way of thinking and not just a bunch of formulas. And people are often mistaking that, oh, you're doing mathematics, so you are under a pile of formulas. But that's essentially not really mathematics. Mathematics should be and is more and more about problem solving, for which you use the language of mathematics, so to say.
That's a nice take-home message. Thank you. Okay, so this was the 6th episode. I want to thank Jan Baetens for the information and Korneel Neysens for the question. Let's meet again for the next episode of Apple Finch Pudding.